Hi, Great Fires kids. Welcome to week 29. You're almost done with our year of studying chemistry and physics. But as you've seen this year, you can't separate out science. All of it relates, and studying physics helps you understand astronomy and geology and biology and anatomy so much better. Studying chemistry helps you understand those same things. And those other things help you gain insight about chemistry and physics. So I'm so impressed with how much you've learned. This week we are finishing off with light. Last week we talked about waves and we had a brief introduction to the electromagnetic spectrum. So your memory work this week is, what are the colors in the visible light spectrum? We put it to Yankee Doodle because I know you boys love to sing, right? Red, orange, yellow, green, blue, indigo, violet are the colors of the visible light spectrum. If you prefer, you can remember Roy G. Biv, like a guy's name, okay? And then for what are the types of electromagnetic radiation? You can say radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma radiation. Got it? Easy peasy. You'll do great at recitations. So this week we're talking about light. It's something that we realized last week we kind of take for granted. What is it? What is it? We kind of touched on some ideas of energy and photons and electricity and magnetism. In the mid-1800s, a guy named James Clerk Maxwell took the concepts of a lot of other scientists. Remember, a lot of science, kind of like when we studied our inventors this semester for history, it's not necessarily that they came up with a completely new idea, but they built on ideas of others and combined them in new ways that helped us gain understanding. And what's amazing with all of this is all of these things point to our Creator God. The more understanding we gain, I hope you understand how thankful we can be for God's creation and His sustaining of it, but also just the beauty of it, how intentional everything is, how beyond our ability to comprehend. Every time we understand something new, it opens a whole field of stuff that we don't understand. We have more questions to ask, right? So James Clerk Maxwell in the mid-1800s was studying ideas of electricity and magnetism, following on the work of Oersted and Faraday. He figured out how to explain light. He found that changing electric fields, so as we have, what is electricity? Moving electrons, right? Changing an electric field could create a changing magnetic field, which would then create another changing electric field, or another electric field, which would then create another magnetic field, and so on. The process repeats in this self-sustaining thing that we call the electromagnetic field. It's endlessly repeating, traveling incredibly fast. So if we think of the energy from the sun, remember God created at the beginning, we learned from the law of conservation of energy, energy cannot be created nor destroyed, it just changes form, right? So think all the energy that exists, God created at the beginning. So when energy travels between 2 points, like the sun, energy from the sun travels to Earth, right? It travels in the form of waves, kind of like ocean waves, like we said last week, except way smaller, 100 million times smaller, most likely. It's a pattern of vibrating electricity and magnetism. Isn't that amazing? That's how energy travels, is on these fields, these self-repeating fields of electricity and magnetism. That's electromagnetic energy, and it travels at over 186,000 miles per second. It's amazing. The light, so I'm going to show you a thing really quickly before we get to our experiments here. I found this a very helpful thing showing the electromagnetic spectrum, okay? And we start with different wavelengths. Over here, these ones can be as wide as Jupiter between peak to peak. Remember we learned our measurements of, we learned peaks and troughs. We learned amplitude is the height of the wave. Wavelength is from peak to peak. And frequency is how many waves happen per second, okay? In a time period. So radio waves can be anywhere from a few feet long to miles long, okay? Typically about the size of a building. What does radio wave sound like? Radio. I know not many of you listen to the radio anymore, but Sirius and XM and all those other streaming services use satellites that use radio waves to send data. Satellites, computers, lots of things use radio waves. Microwaves are our next one. What does that sound like? Oh, it sounds like microwave. Microwaves are measured typically in like centimeters. At the longer end might be feet, but we use a microwave. It's energy that is transmitted in a wave into your food to heat it, right? We use it to cook food. I had heard at one point, you can research it at home, that the design of the black stuff on the glass of your microwave is actually meant to prevent the microwaves from coming out of it. But I don't know that energy from being transmitted outside of the food that's being cooked inside. You can research that. It would be interesting. What's cool, you can also use microwaves to transmit data. Like basically we use that energy wave to send information. You guys, that would be super cool to research at home and learn more about. We also use microwaves for weather radar because those wavelengths can penetrate clouds and smoke or rain. Kind of cool. The next one is infrared, and it can be either far infrared, which is like thermal, meaning heat, or near infrared. As I mentioned to you guys, I'm going to actually grab my remote so I can show you. Hold on for 1 second. And I'm going to show you. When you look at the front of your remote, you don't see anything. You can try this at home. Try holding down the volume button, and you see nothing. But watch this. That is infrared light. My phone can pick it up, even though my eyes can't see it. And some animals can see infrared light, like foxes. Also, the military, it's super helpful. Nowadays, I bet they're using it for thermal temperature scanning, too. But my husband used to use night vision goggles when he was flying the helicopter at night. And it allows them to see things at night that you cannot see with your eyes, because everything that, as we metabolize, we give off heat energy. Kind of cool. Do you see how all this is tying together? Okay, then after infrared is visible. What does visible make you think of? Something that you can see. This is the one little bit of light energy that we can see with our eyes. The wavelengths are between 390 and 700 nanometers from peak to peak. That's exactly what our eyes can read. We can't see anything else. God designed it that way, right? The wavelength from peak to peak is approximately 1/100th the width of a human hair. The frequency we measure in hertz. It's 430 to 790 terahertz. That means billion hertz. That's a lot of frequent waves in a given second. So this is a really cool display. Then they also have ultraviolet. Some insects can see ultraviolet light. We cannot, right? But you can use ultraviolet light. Sometimes, that's what causes sunburns from the sun's radiation. Some ultraviolet rays are able to make it through our atmosphere, probably the ones that are closer to visible light. Our atmosphere prevents a lot of radiation from the sun from coming through. That's where our ultraviolet, X-ray, and gamma rays from all of the nuclear explosions of the sun. Remember all the stuff that we studied in astronomy of everything going on the sun that emits all this energy, but a lot of it is blocked by our atmosphere. Otherwise, we would die, right? But some UV rays can get through. And that's why you can get sunglasses that provide UV protection to keep your eyes from being damaged. You can wear sunscreen that blocks or absorbs those UV rays to keep you from getting sunburned. Otherwise, the UV rays can pass through your skin and cause a sunburn, and eventually can cause cancer, right? Then the other waves, and the absorption is just a matter of that size of that wave, that it can prevent that size wave from getting through. Next is X-rays. What do we use X-rays for? Yeah, at the doctor's office, they can use X-rays to actually pass through your skin, pass through muscles and organs, and take pictures of your bones. Gamma rays can also be used by doctors. They can use it for diagnostic tests because it can scan through things, but it can also be used to treat cancer. These things can also be dangerous. So like when there's a nuclear explosion, it releases a lot of gamma rays, which is what can penetrate people and cause a lot of illness, right? Supernovas also give off gamma rays. This is the highest level of energy, of light energy. So cool, you guys, how God made all of these, and by understanding them, we can use them for different things. So amazing. But let's get to the fun stuff, you guys. So how do we see light? Have you ever, you guys, there's so much to think about that we take for granted. So you can either see light directly, where light comes into your eyes directly. Like I can look at a light bulb and the light doesn't reflect off anything. Otherwise, everything else, like seeing this chair, is a matter of light coming from a light source, either the sun outside or a light bulb, hitting the chair and reflecting back to my eyes. Okay. What's cool, we're going to get into it, is a matter of colors, that white light is made up of light. The visible light spectrum has 7 colors. Remember our Roy G. Biv. When it reflects, red has the longest wavelength, violet has the shortest wavelength. And depending on the molecules in any item, it could be my skin, it could be a chair, it could be water. Light behaves differently based on those atoms and their ability to kind of have the frequency with which the atoms are vibrating. And so then some of it will get absorbed in to the item and some of it will reflect off, depending on the wavelength. So amazing. If it reflects off every color, we see white. Okay? If it absorbs every wavelength of color, we see black. Some things absorb certain frequencies, like chlorophyll is a pigment in plants. Remember, we've studied this in botany, when sunlight hits the plant, all of the red types of wavelengths get absorbed. All of the blue type wavelengths get absorbed. The only ones that reflect back are the green wavelengths right in the middle. That's why plant leaves look green. Kind of cool, right? So it just depends on which parts of the light are absorbed. You guys, one cool thing is there are 3 main colors of light. Okay, there's your primary colors are red, green, and blue. If you mix red and blue paint, what are you going to get? You'll probably say purple, okay? I'm going to show you guys this on an experiment. I'm going to do this red and blue sheet of paper, and I'm going to connect it to a motor to spin it together really fast. And sure enough, we get purple, right? And we kind of got a magenta color. If I do blue and green paint, what do I get? Kind of a teal color, okay? So, yeah, this is called cyan. Okay, if you study any kind of computer programming or anything, you'll get very familiar with these things because this is how they make all of the colors that we print or see on screens, is by combining these colors in certain ways. Different amounts of red, green, and blue. Okay, if we mixed red and green paint, what would we get? Are you going to say brown? Yeah, I bet you're going to guess brown. That's where light is different, you guys. When we mix red and green light, this one doesn't turn out perfectly because I think my color red marker was not good enough. You're going to end up with kind of a yellow. Mine is kind of a muddy yellow because my red was not a great color. Red and green light makes yellow. So cool. If you guys prefer crafts over science, there's actually some cool things you can do with this. I got this kit from the Mint Museum. They have a great program of having free art kits to grab at the museum. You can go any Wednesday evening for free. But you can also get this at the Dollar Tree. You can buy different colors of cellophane paper. So I have blue, I have red, I have green, I have yellow. And you can get a piece of contact paper that's sticky on one side, okay? If you prefer, also at Dollar Tree, they have like self-laminating sheets. This is a 3-pack for $1. And what you can do is cut different amounts, and you essentially make a stained glass. And wherever they overlap, they're going to make a different color. Like I have red and yellow. and it combines to make kind of an orange, right? Or if I have red and green, this one does, it's kind of a yellowy brown again. And I have my red and my purple, red and blue, and I kind of get purple. So kind of a cool way to incorporate your science and your art. Always fun. Another fun project, you guys. So with light, another thing that you guys obviously know this already. I'm gonna actually show you. I also have this cool stick that it has different colored LEDs. Now just the red is lit up. Now just the blue is lit up. Now just the green is lit up. Okay. Oh, it shows up poorly on my phone, but then I can combine them. And so now I have yellow, and if you look closely up here, which you can't see on the phone, only the red and the green LEDs are lit up, and it makes my thing yellow. Now I have cyan, and it's the blue and the green lit up. Now I have magenta, and it's the blue and the red lit up. Kind of cool. And then if I turn it on one more time, all of them, the red, blue, and green are on, and it looks white. So kind of cool. You guys can play around with that. Another thing that is fun to play with is refraction. I love the little things that you can get. This actually makes me think of the movie Pollyanna, which Holly loves right now. You can buy jewels at any craft store, or some will sell prisms. And the hard thing is you want to do this with direct sunlight and a white wall that's not in direct sunlight. But you can have the sunlight hit the prism on one side, and you'll see that it splits the light into the 7 colors. The 7 colors kind of run into each other in a rainbow because of that aspect of the frequency or the wavelengths. As red gets very close to orange, it's kind of blurred into orange. As orange gets close to yellow, it kind of blurs into yellow. And you can split it either with a prism. I've also done this where I take a container of water, like a Corningware dish of water. I submerge wow, that's funny. I feel like I'm at the dentist where you can see up my nose. Sorry, that's silly. You can put a mirror in a Corningware dish of water. Go in a dark room and use a flashlight, not an LED flashlight. Make sure it is a regular bulb that puts out white light. Shine the bulb through the water at the mirror, and it will reflect off a prism of all 7 colors. Kind of neat, right? The hard thing with teaching this lesson today is that you can't necessarily do it in a dark room, right? You can also buy these cool glasses that refract the light so that when I look at the light bulb, I can see all the rainbows from it. So cool. I think God gave rainbows to us as a gift. I mean, obviously we can read the story of Noah, of God's promise, but what joy it is when you get to see a rainbow after a rainstorm, isn't it? Such a beautiful thing. I've actually seen a few times where I've seen a double rainbow based on how the water refracts light in the sky. It forms a rainbow. Another thing to know, I'm going to grab one more supply, is wax paper. There you go. Okay, so, and this is helpful when we're studying astronomy to understand this concept. Some things are translucent. Light passes straight through them, and not much of it is absorbed. So that's where air, for example. Other things are opaque. I'm opaque. Light doesn't pass well through me. Instead, it just absorbs or is reflected off of me. Other things are translucent, where light some is absorbed and some comes through. Make sense? So the more we understand about light, the more we can use it. One cool experiment that this helps us also understand the atmosphere. I'm really thirsty. I think I'm going to have a drink. Oh, just kidding. It's part of our study. Notice what happens to my straw at the point where it hits the water. Doesn't it look different below the water than it does above? That's because of the way that the water is refracting or bending light waves. Isn't that cool? I love also putting like a coin in. I'm going to see if I can help you guys see this. Let me see. Do you see how at that angle you can see different sizes of coins? It's only one coin, but you see it from the side and above. So you're seeing two images of it. One is bigger than the other. And it's just a matter of how light waves are bent by the water. I want to try another thing. Another thing that's fun to try is using mirrors. Mirrors make lots of fun. If you take, maybe this summer, a toilet paper or paper towel tube, you can buy some mirrors at a craft store. Sometimes the Dollar Tree will have them. And you put them in a triangle shape, okay? And I covered one end of my tube and just poked a hole in it. And then you can make a kaleidoscope out of it, okay? So you just look through that hole. If you want, you can put a cup of beads or something else colorful at the end and turn it, and you have a homemade kaleidoscope. Another fun one for you boys to try, girls too, it's fun for anyone, is take a tube. I made a box shape just out of spare cardboard, and I cut a hole at one end with a slit on the side. Okay, so I cut a square hole and a slit the size of a mirror, and then at the opposite side at the bottom, I cut another hole, and the same side I put another mirror. So my two mirrors are facing the same direction on one side, and I have a slit down here by this mirror and a slit on the opposite side up by this mirror. And when you angle them, you've now made a homemade periscope. You can sit in one room and don't spy on people, respect their privacy, but you could use this to like spy on your dog or an animal outside. You can be in one room and stick your periscope up against your eye, or maybe over the couch you can watch TV. The mirror will allow you to see something, even though you're hiding behind a wall or the couch. The mirror reflects the light from whatever, and you can see it. Another thing that's cool is we can bend light using lenses, concave or convex lenses. Like that's how you bend glass. So this is bent in. Hold on for 1 second, Holly. I'm recording, babe. And you can use that for eyeglasses, but not just eyeglasses. Cameras and camcorders, for example. Let me see if I can find my. This is a fun thing to get for your phone. Maybe you can do this summer. We use it for magnifying glasses, microscopes, bend light so we can see it better. And then telescopes, binoculars, lots of things. These are all called optical equipment. Optics, fiber optic cable. Have you ever heard of that? That's used to carry light waves, right? But I love these things too. You can buy these little lenses to attach to your phone, and it changes the picture that you take. It can zoom in or bend it in a funny way. So another thing that kind of ties in with what you guys have been studying with Thomas Edison. Remember, what did he invent? The light bulb. Great job. That you can have hot light and cold light. So source of light, basically, actually, let me explain this to you because it's super cool. What are our parts of an atom? Do you guys remember? Protons, neutrons, electrons. And remember, the protons and neutrons are in the nucleus and the electrons are on the outer shells. What's so cool? Okay, so we provide a source of energy, right? The energy can excite the electrons and make them jump to a higher level. Remember, there are shells of electrons, but then the atom's not stable, right? Because each shell is supposed to have a certain number of electrons. So energy comes into the atom, excites the electrons jump up a level, and then they're like, oh, no, it's really wobbly up here, and they fall back down. But the energy, what happens to that energy then? It can't just disappear. That's when atoms emit energy, light energy, photons. When the electrons are unstable, they got a lot of energy, they're up here, but they're so excited, and then they fall back down. They emit that extra energy as light. So cool, isn't it? So what was I about to show you? But light always travels in a straight line. That was my last point that I wanted to share with you guys before we're done for today. And this one we're gonna have to go in the dark for. Okay, let me grab my supplies and we're gonna go into the dark. Where did I put it? So you guys can do a similar thing. Please always be careful with a laser pointer. You can do this with a regular flashlight, but a laser pointer makes me feel like James Bond or Spy Kids or something like that. You'll need baby powder is easiest. You can also use cornstarch, but it's harder to spread it out. And a laser pointer in a dark room. Make sure you never aim a laser pointer up in the air or at a person. Even though the light can eventually diffuse, it can be dangerous, okay? Similarly, be careful that you don't breathe in the cornstarch from the baby powder. Okay, we're going in the dark. Okay, I'm going to turn on my laser pointer, and then I'm going to spray some of this baby powder. Okay? Let's see if we can see it with this. Oh man, it's really hard. I'm gonna turn it around. Let me see. Do you guys see that? Let me see if I can flip around my camera. Let's see if you can see it. There we go. So amazing. So if I just point a laser pointer normally, you only see the dot at the end. But by spraying the cornstarch in the air, the baby powder, you can see that light travels in a straight line. Isn't that amazing, you guys? So as the cornstarch starts to go out of the air, you'll see less and less of this. Okay, so if I come away from the cornstarch, you won't be able to see it. Hardly at all, right? So light travels in a straight line. This is different than when we were studying sound waves. Think about it. If you're in your room and your mom shouts, "Come down for dinner," does her sound travel in a straight line? No, it spreads out, right? Light, however, typically travels in a straight line. There are ways to diffract it, right? But now you guys know a whole lot about light and electromagnetic radiation. You know how photons are made. You know about how to control light. You can block it with using opaque or transparent materials. You can reflect it or scatter light using mirrors. You've learned about how light travels in a straight path, but it can be bent using refraction, right? And we also learned about absorption, how different pigments absorb the different frequency wavelengths of light, and that's how we see colors. And lastly, your hot light and cold light. This is where our point about Thomas Edison. When he invented the light bulb, he heated up a filament, and that heat excited the electrons and made them give off photons. On the flip side, there are other ways of exciting electrons, and that's where we get fluorescence. All of these are types of luminescence, and some of you might know the word bioluminescence. Remember, there are different ways of exciting electrons within atoms to make them give off light. Some of you may remember from week 6. What are some signs of a chemical reaction? One of them was light, right? How in here, we break the little glass vial that has a chemical that then reacts with the other chemicals in here, and it gives off light. Now you understand that that is a matter of the electrons being excited. You guys, most importantly this year, there's an even more important type of light. One that brings brightness to a dark world. I want you to remember that you are the light, carry the light of Christ in you. Let your light so shine before men that they may see your good works and glorify your Father in heaven. I hope you have a great summer. Thank you for spending this year with me. I'm going to cry because I'm going to miss you guys so much. Have a good one.